Okay. Don't say anything bad.
Tag team off the ropes.
Yeah, right. I'm weighing in at. Okay, so we're good to go. Yeah. All right. Hi, everyone. My name's Nick Parker. We're here presenting about enhancing password-based key derivation techniques. I work with Zetetic, based out of Iowa.
And my name is Stephen Lombardo, also with Zetetic and based out of New Jersey.
There we go. So one of the projects that we work on, spend a lot of time on, is SQL Cipher. Is anyone, just to get a feel for the room, is anyone familiar with SQL Cipher at all? Okay, a few. Also, SQLite, is that? Okay, so a few people are familiar. So SQL Cipher is based on SQLite. It's an open source extension to SQLite that provides full database encryption. So, saying that SQLite is in an embedded database, and so it has a very large platform target, if you will. So if you want to look at the different languages and platforms that it would run on, we basically operate on many of those. C, C++. I won't read the whole list, but there's a good chance that if you develop in that SQL Cipher is going to run on that platform. So we often find ourselves with kind of a broad spectrum of users that use that for various means. They both operate in the mobile and desktop space. But our focus today is specifically on securing user data, where the user provides a portion of the key material. So we're just going to take a quick look, a high level, of how SQL Cipher works. So there's transparent interaction as a client developer. You don't have to deal with any of the encryption, the decryption process. It all happens on the fly. So you have a client database API that you'll consume, and everything just works. You provide the passphrase, and you get your data based on your queries that you operate on. When you insert data, we store that, we encrypt it for you automatically. It's on the fly. So in other words, the entire file is encrypted. However, if you are querying for a certain portion of data out of your file, it'll only decrypt the amount of data that it needs to retrieve that for you. We have a crypto provider system, so structured within the library itself allows us to swap out different crypto providers. By default, we use OpenSSL. We've ported that then to use Common Crypto for iOS as an example, and then libtomcrypt for other platforms where OpenSSL isn't appropriate. We use a standard KDF, PBKDF2, and so historically, sometimes people will ask us why don't you use other key derivation approaches? Scrypt has become a very popular approach, and SQL Cipher predates scrypt. So to visualize the structure of how data is stored, every database when it's created gets a unique per database salt, and then the actual database stores these like opaque blocks of data in pages. And so you've got your encrypted block, a unique initialization vector, and then a MAC for the data. Can everyone hear me okay? I kind of keep coming in and out. Yeah. So with that said, I want to take a step back and look at how SQL Cipher has evolved over the years. Okay, so when we initially released it, we had a iteration length of 4,000 as it relates to computing the key through PBKDF2. And just recently, I think it's maybe a little over a year ago, we upgraded the library and changed it so that it used 64,000 iterations. you'll note that while we did timings, on various devices when we made those initial configurations, and then when we upgraded, they were still somewhat arbitrary. We verified that they didn't take too long. They were still arbitrary. So what we looked at is, maybe we can do things better. And so we think we have two approaches that are applicable in the context of SQL Cipher. So the first one is an adaptive key derivation approach, and the second one is multi-factor hardware token integration. Okay, so I'm going to put the mic down for a split second. Oh, it doesn't. Hang on. Good, there. If you can't read that, so this story kind of predates. It goes back a couple years. 2 years ago, I was down in Brazil, and I had a conversation with Jacob Applebaum, and he kind of came up, and we were talking about SQL Cipher, and he mentioned that, hey, I've got an Android G1. It's a fairly old device. It doesn't have a lot of computing power, but I have a new Android device that's much better. And it'd be fantastic if you could take an approach that you don't use a static key derivation, work factor, and actually take advantage of the hardware that I have. So that kind of got us thinking, and we got busy, like everyone does. But we've taken that to heart. So let's just take a look at, what are some of the problems that we have with this static KDF length, right? Both desktop, most of the time, how many of us here develop for multiple platforms, both desktop and hardware and mobile devices, right? So the hardware specs on those vary drastically, right? Okay. The technology continues to evolve over time, right? iPhones are able to take advantage of GPU acceleration when they deal with crypto primitives, and the reality is that while we have tools like Hashcat that can do amazing things, there are different security requirements for different types of applications. The user experience may change, right? So you may be dealing with highly sensitive data, and a wait time of maybe 10 seconds is appropriate when accessing data, whereas other applications may need to be more snappy. So if we look at the adaptive KDF goals and kind of frame this in the context of PBKDF2 as it relates to what our goal is, we'd like to provide fast sampling across all platforms. So even on that G1 device, we would like it to be just as fast, relatively speaking. We want to be able to compute the ideal work factor and limit it by time, right? Because ultimately, we don't want to have to take into account the various hardware components that might play into how it would operate. And we would like to allow that sampling to occur on any of our platforms that we support. So what we came up with is an approach to allow the computation of the KDF to run automatically on the device. It's constrained by time. We have a default value, and it's tunable. So what we're looking at here is just an example from the SQL Cipher command shell, allowing you to interact with the KDF computation routine. So here's just 3 examples where we initialize a database, we'll key the database, and then we ask it to compute a KDF work factor. Now these are all run on a MacBook Pro 2.3 gigahertz device. And in the default situation where we run for 1 second, I was able to compute just a little over 1 million iterations. In the scenario again, where I allow for 2 seconds to compute, I get a little over 2.2 million. And if I constrain it down to, say, half a second, it's 575,000 iterations. So that's, just in reviewing that, that's quite a spectrum of change from our static value that we've had before. So here's just a table of various devices where we've sampled across hardware and simulators, emulators, and phones. And you can see that while there are some devices like the Android emulator are somewhat close to what our static values are, all the various devices, we're really doing a disservice to users in not taking advantage of the hardware that's available to them by using a static key or a static work factor. That's for 1 second. So when we start talking about computing a work factor on a per device basis, kind of introduces a new set of challenges that we didn't have to deal with before. Previously, we had a static key, or not a static key, excuse me, a static iteration length, and so the client developer wasn't responsible for maintaining that. But now, any application that consumes this would have to track what that work factor value is in order to be able to access the database again. So persisting the KDF work factor becomes important. We can, in fact, and that leads us to our next slide. Yep, it's a very good question, very poignant. So visually, we've got two pictures going on. I'm going to describe the far right picture first. So SQLite has a series of layers, and at the very bottom layer, they implement what's called a virtual file system. So it's their abstraction layer to interop with various operating systems, with reading and writing of files, etc. And so we have a new SQL Cipher virtual file system that acts as like a facade around the underlying virtual file system and allows us to control writing a header, which will persist the information that's relevant to us. So a computed KDF work factor on device would automatically be stored within the database file itself. Everything else continues to remain the same as the previous example gave, where we get the database salt and then our pages of data. So it essentially gives us a means to have an offset point. So, kind of forget about all this data, start here instead of here.
Is that where you're storing
No, so historically, SQL Cipher will ship with default KDF work factor lengths, default ciphers, page sizes, and all those things are adjustable from a client library perspective. So you had two options essentially. You could use the defaults, which is generally what people would do, or what we would recommend. And the other option was to change them. And if you changed them, the client was responsible for supplying what those values were before you interacted with it. So you would open your connection to the database, supply your configuration parameters, and then interact with it.
So does this new header include all of that stuff now? The client's no longer responsible for remembering this?
Right. So the question, if this new header includes all of that information, yes and no. So this is an experimental branch right now. We have almost all of that information stored. However, some of that information there's more information that we'd like to include in that header. So it's not finalized yet, but it's pretty close. So the idea here is to make it as simple as possible for the client developer to consume the library and still take advantage of being able to compute a new work factor. So if we kind of take a look at the pros and cons of being able to compute an adaptive work factor, the pro here is that we get a sample across all platforms. We can constrain it by time, right? So it's consistent by time, which is really from an end user's perspective what's important, whether or not they have access within a half of a second or 10 seconds. And we can sample that across all devices. PBKDF2 being, our computation routine focuses strictly on doing a linear calculation. So the cons is cross-device performance. So what that means is, for example, with Jacob Applebaum, he has his G1 and he has a new Android device. And the work factor is going to be dramatically different between those two devices. So, if you take my MacBook Pro, I can compute a very high work factor. And then if I try and interact with that database on a device that has poor hardware performance, the time at that point does not scale well. This also introduces additional complexity within the SQL Cipher codebase. So that onus falls on us.
Can I ask a question?
Absolutely.
So, did you watch for system load at all? Like if the system was heavily loaded when you did the benchmarking?
So the question is, if we watch for system load, to answer that, yes and no. So there are certain environments, in particular. So SQL Cipher runs on Android, on the Android platform, and one of the things that we've seen over time, and it's I don't know if I think it's specific to the Android platform, but it's also maybe partially related to the client library in terms of how things work. You've got a Java layer, a JNI interop layer, and then a native layer. And so there's a lot of things that are kind of at play. And so we've seen scenarios where, opening a connection to a database where, and that first operation where it actually has to derive the key can take considerably longer. And the fact that you have devices that have a very broad spectrum of behaviors in terms of what they support, you do see things like that. Generally speaking, I would say you don't on other platforms, but based on that is we use the information that we've seen as we profile it to determine what our default recommendation is for the default time period. Because I also work on Strip, which is a cross-platform password data manager, and so we experience those same things as well in terms of the performance and that user experience. So, but again, it's tunable, I guess, to the environment that you put it in.
If you're still taking a question about this part.
Yeah, sure. Go ahead.
I'm actually just going to say, talk to you later. We did address exactly these same issues, and I'm happy to talk to you about it.
Yeah, sure. Absolutely.
Our solutions and the things we've run up against.
Yeah, sure. Absolutely. Yeah, I'd love to talk to you about it. Anybody else? Or we can take questions later too, or offline. So.
Thanks, Nick. All right, so the next thing that we started to take a look at with, kind of enhancing our standard key derivation functions is how we might be able to integrate a multi-factor scenario where getting access to a database is no longer just about one factor, which is the passphrase that you know, but there's also the requirement to present something that you have, something on your person, and that would be a hardware token. So stepping back briefly here, no? Okay. So stepping back, we've got our current KDF, right, which is PBKDF2. And the inputs to this function are essentially the database key, which is provided by the user, and that's the passphrase. And we have this random database salt, which we store, as you saw from the picture that Nick talked about, we store it right at the front of the file. And that's generated randomly for every individual database that's created. And then we have this new adaptive work factor. And those all get combined, passed into PBKDF2 to generate our encryption key, which is actually used to encrypt the page data. So what we'd ideally like to do is say, well, how can we add a hardware token to the mix? And we have some requirements for it. So ideally, we want something to meet our requirements that would work offline. So there's a lot of sort of going back to the previous talk about what is authentication versus encryption. There's a lot of multi-factor authentication solutions out there. You've got, TOTP, you've got, YubiKey has one. There's, a variety of them. But one of the key things that is pretty important is there's always another party that's doing authentication. Typically, you have to have some sort of network connectivity. And we really don't want to put that requirement in for a system like SQL Cipher, where there may be specific requirements for offline data access, or maybe you don't really trust any other parties to do authentication. So that's really a critical one. And that leads us to, how do we interface with the hardware token? And we'd like it to be something simple, USB ideally. In the best case scenario, the tokens would be very widely available. So, something that you could really go out and buy, kind of a commodity product, and one that provides onboard crypto so that we're not, introducing yet more complexity into the SQL Cipher database. And since we're going to be doing some sort of hypothetical crypto operations, and it's going to be tied to the token, we need to have secure key storage. Generally, that means that you can write to, whatever your token is, you can write a random key to it. Once you do that, you can't get it back off. So if I lose the token or something like that, somebody can't extract the key off of it. If it's multi-use and inexpensive as well, then that's even better. So there's a couple of different, there's actually more than one hardware token available that will meet this kind of requirement. And the first one is a YubiKey. And is anybody familiar with YubiKeys at all? Okay, cool. So yeah, YubiKeys are pretty neat. They're these little, USB hardware tokens. They look kind of like this. There's actually two form factors. One is a big one that's kind of intended to be carried on your keychain, hence the key. The one that you have over there, the little tiny one, is called a Nano. That's actually intended more to be left inside of a USB port. You kind of jam it in there, and it has a very low form factor, and you don't take it out. You can get it out, but you generally leave it in. So we have, so YubiKeys have been around for quite a while. We've been having kind of a long history with them. We did a little open source project a while ago that got us thinking a little bit about this, which is a project called One Time for YubiKey. And what we wanted to do with that, a brief departure, is allow you to do time-based one-time passwords like your Google two-factor authentication, where your secret is actually stored on the YubiKey. So we got into looking at the interface, and it has a suite of onboard crypto functions that you can call. They're practically indestructible. Like, you can run over them. They're waterproof. People routinely write in about how they toss them in the washing machine and then dried them for 3 hours and they still work. And they're inexpensive. Individually, they only cost like $25 for the larger form factor and maybe $40 for the smaller one. But if you buy them in bulk, the pricing goes down very considerably there. And the other one that we identified is kind of a new entrant called .plug or plug up. And these have a very similar kind of form factor. They look a little bit like this. They actually ship them on what looks like a smart card, where it's kind of carved out, and you pop it out yourself, fold the little tab over to make it thick enough to fit into a USB port. The tricky thing here is they're primarily available, I won't say only available in Europe, but primarily available in Europe. They don't have a really good solution for shipping to the US now. So while the tokens themselves are only about €8, when we ended up getting them, they were kind enough to give us some for free for this particular talk. The shipping costs on that ended up being like about $110 to get to the US. So it's a little bit, they always get you on the shipping, right? So that's a little bit skewed, but I think they do work and provide very similar functionality to what YubiKey does. Really with this common denominator that we're taking advantage of, and that is the fact that they both provide an onboard HMAC SHA-1 implementation that's callable via a challenge response API. So the idea is that you program your key with one time, you write out your random key data, and then your interactions from that point forward with the hardware token is, I'm going to give you some data, and you're going to sign it, and you're going to give me the data back. And you're going to use the secret key that's on the device. I don't know what that is anymore. If you get the device, you're not going to know what it is either. So our simple implementation is really to use this onboard token key and HMAC, and we don't want to fundamentally change PBKDF2, right? We don't want to fundamentally change the key derivation algorithm, but we want to say, well, how can we enhance it a little bit? And the solution that we've come up with that works really well in this case is to permute the database salt before we use it. So if you think back to the approach that we had before, where the salt is sitting there, public data in the database header, we're actually going to take that salt and using what we have a provider callback in SQL Cipher, we're going to send the salt into the token, say, HMAC this with the secret key that's on the token that we can't get to, and take that data out and pass that in to the key derivation function. So our sort of simplified MFA process adds in these two factors, which is the token key, secret, and HMAC SHA-1, and uses that to operate to calculate the actual database encryption key. So the general results here, really pretty positive. In fact, you can generate a random key. You can plug it in on both devices. There's different APIs for the two devices, but they're actually interoperable. So you can plug the same, key onto your YubiKey and put it onto your, dot plug. You could spin up 5 or 6 of them if you're worried about having backups of that hardware token. Put them in a safety deposit box or something of that nature. And you can only open the database if the key is in place in the USB port. In fact, with the more advanced features like the YubiKey has, where the challenge response API, there's actually a button on the YubiKey. You probably can't see it, but there's actually a touch sensor on it. You can program the YubiKey in such a way that in order to complete the challenge response, you have to touch it, blinks, and you have to touch it for additional security. So there's these kind of built-in functions as well, but they are interoperable. It provides a very simple implementation. You can't extract the key from the token, and importantly, in this case, there's different ways that you could do this, but one of the important factors here is that we're never really disclosing anything to the hardware. We're not technically trusting the hardware other than to generate a valid HMAC. We're never sending in anything to the hardware that's secret from the database perspective. We're not giving the hardware our password, our database passphrase or encryption key. We're only giving it this otherwise public data and then using the response. So even if the hardware was tampered with or somehow got swapped out and you happen to get a YubiKey that stores every piece of every message that gets sent into it for later extraction, you're never exposing any actual secret data to the hardware token. Mm-hmm. So that's a fair concern, and if it did output zeros every time, then you would, at worst, you would still have the protection of the database encryption key. So you'd still have that operation on it. So, but yeah, if the hardware was tampered with to the point that was always outputting, a static value, then yeah, you would lose the randomness of the database salt.
Question.
Mm-hmm.
Is there a way to verify whether or not it's tampered with in that fashion?
Certainly, yeah, and actually we did that as part of part of the project when we were kind of going through it. One easy way, we don't have it coded into the library right now, but one easy way to do it is to take and verify when you flash the token. You can actually, what the key was at that point in time, and you can execute an HMAC operation with a known good library like OpenSSL and verify that you got the same value out. So we actually did that during the development process, and it's in one of the revisions. It's in the code. There's a link that we'll publish to GitHub for it.
Would you be able to put
that in a separate project as a library by chance?
Yeah. Yep. Absolutely. I mean, I would probably encourage, at that point, the way that you could verify that, and you can't definitely verify it, that it will always return in every case, but at the point where you flash it would be a good point to do that. So both of these devices have an API that you use to flash them, and at that point, you can take whatever random data that you're going to put in, flash it to the device, test that you can get a signature back, validate it with a third-party implementation, an OpenSSL or HMAC, Common Crypto, whatever the case is, and verify that you're getting good data out of it. Yeah. If it then at a later date decides to do something bad, then it's tricky. So cons here, I guess that the big ones, USB is required for this implementation. So that does kind of limit it to platforms where you have a USB port in place. It makes it difficult to do it on like iOS devices or something of that nature, and in a lot of cases like Android devices, your mobile platforms. But we look at that as a con for right now. But this is sort of an experimental feature, something that we're thinking about, not necessarily something that people are going to necessarily go out and do today. And a lot of these device manufacturers are starting to go to alternate interfaces. Even YubiKey has they have a token which it does NFC. So you have a wireless option to do that challenge response function instead of having it plugged into the USB port. So this is something that as the technology improves and there's additional options that are available in the tokens, this stuff will mature, and it'll probably be more practical to use this sort of multi-factor encryption scenario with mobile devices. The other cons really involve the fact that you've got a lot of additional code involved, so it's complexity, right? There's custom code that has to be implemented for the SQL Cipher side. There's callbacks, that actually do the work of interacting with the APIs, and then there's the API dependencies themselves. So just to kind of give you an idea, to implement this for two different functions or two different hardware tokens, you need like the Yubico C API, you need the Yubico YubiKey personalization API, you need the .plug API that has a dependency on OpenSSL, so you need to have that in place. They both have dependencies on libUSB, and then those have dependencies on, at least on the Mac, on IOKit and whatnot. So you've got a pretty steep dependency chain involved with everything related to running it. But once you get it up and running, and you can take care of that in an automated build process. But there is a certain level of complexity that's inherently involved with adding a hardware token into the mix here.
So dependencies available on all platforms?
Yes. Well, outside of iOS and Android, so outside of the mobile, but they do support Linux. Both platforms support Linux, support Windows, and support Mac. So for any desktop, environment that you would choose to do this, where you might have, some highly sensitive data that you want to put into a SQL Cipher database, this would be doable. Yeah.
Isn't there some sort of API or library that would work for like the NFC version?
Yes, there is an NFC version for Android. I don't have a NFC-enabled YubiKey, but there is an NFC API for Android. And actually, there's a couple of sample applications that Yubico has published. I think one that uses one of their NFC tokens for encrypting your OpenPGP keys. So you have to have it in there. So it's definitely something that is feasible, to put into place, but not something that we did as part of this experimental feature edition. Cool. So that pretty much covers it with the multi-factor there. If anybody has any questions, we'd be happy to take them. We have more information up here. SQLCipher.net is the website for SQL Cipher. As Nick mentioned right at the beginning, SQL Cipher is an open source project. So you can go to GitHub, you can check it out. All of this work related to the adaptive key derivation is all on a branch there called VFS. That's related to the virtual file system that we had to implement to store the adaptive key derivations, but you can check it out there. And some of the kind of rough, sample code that we use to do the multi-factor encryption is available out there as well under the SQL Cipher MFA repo. Any questions overall? Sure.
There is a open source, open hardware crypto stick out there. I know it was linked in Google Summer of Code, and while it's not really commonly available, it is something to look at as another possible alternative.
Cool. Yeah, I think if you look at the MFA project and you kind of see how it works, it's really actually very simple. There's the provider interface in SQL Cipher essentially exposes a bunch of callbacks for common things that it needs to do. So there's a key derivation callback. There's an encrypt as data callback. There's here's a HMAC callback that we use for generating the max on the pages. And then, there's one in there for this kind of salt permutation and whatnot. So you can take that and hook into it. So as long as whatever token that you happen to have, in fact, it wouldn't even have to be a token if you didn't want it to. If you wanted to rig something up that makes a remote call, to a remote call to something, maybe plugged into the device, an iPhone or whatever the case is, you could do it, and you just hook into that. As long as it's generating output that kind of diversifies the salt coming in and changes it, then it would work with this approach. So it's very open for other implementations, and it'd be kind of neat to see that kind of stuff crop up. I mean, ideally, for us, SQL Cipher is kind of half. It's half. Business, because we use it in our own software. We use it in Strip. We also license it to other companies. It's open source. We have commercial edition stuff. So we license it. We do support for it. It's part of our core business. But it's also sort of a platform where we experiment with ideas, like this. And if they start to take off and people are interested in it, we then tend to focus on it. So it very much is like requirement-driven development for us. What is the community interested in, and are people using it? Is it something that makes sense for practical implementation? And then we kind of take these features and run them through, and they stop being experimental and start being real. Cool. Any other questions? All right, great. Well, thank you very much for your time. Oh, one other quick thing. If you have any other feedback or discussions about SQL Cipher, you can hit up that URL as well.
Or talk to us.
Talk to us whenever.
Yeah, just grab us.
Don't.